Okay, thank you for the introduction. My name is Jia Hui Ho, and today I will introduce our work, SignSpeaker, a real-time, high-precision smartwatch-based sign language translator. And released by the World Health Organization, there's over 466 million people have their disabling hearing loss, which include 34 million children. Roughly 1.1 billion young people are at risk of hearing loss due to the exposure to the noise in the recreational setting. And it's estimated that by 2050, there's over 900 million people will have their disabling hearing loss. And the hearing impaired always will use the sign language to translate with others. However, there is a gap between the hearing impaired and the people with a normal hearing, since actually most of us do not know about the sign language. And this is the reason that's why we need the help of the sign language translator. And after collecting information of the sign words performed by the users, sign language translator can analyze and interpret it into text, which can be understood by the users. And in this work, we focus on the American Sign Language, since American Sign Language is one of the most common sign language in the world. There are mainly two methods to implement the translator. One is the visual-based. They analyze the motion and gestures from the photos or videos. And the other methods are based on the signal and motion sensors. Multiple sensors are used to check the motions of the hands and gesture. However, this existing words has some limitations. For example, that's in the visual-based methods, the lighting, background, and the distance between the camera and the users are need to carefully design. And also, in the current sensor-based words, to get a high precision, there's multiple expensive, sophisticated, and dedicated devices I need to use. This may result in the poor probability and also some unexpected safety hazards. And what's more, some words may involve some video processing, and this is time-consuming. And we find that for different sign words, the accelerations and rotation speeds in three directions collected from a smartwatch actually are different, which means that we can use this sensing data to characterize the sign language. And in our work, we designed a normal American Sign Language system, which is used to continuously recognize whole sentence using the portable and lightweight devices. And this can be used anytime and anywhere. To achieve such a goal, there are several challenges. Firstly, the sign language always involves some fine-grained finger checking, which is micro and hard to recognize if directly based on the coarse noising sensing data. And the second is that there is a wide range of the unexpected movement between two signs. For example, the sign for the father is repeated tapping the head in the forehead, and the sign for the name is performed in the neutral. That's if we perform these two signs in succession, there's one more movement from the forehead to the neutrons will be introduced. And lastly, individuals can perform a wide spectrum of signs, and our system should support the diversity of the individuals and their devices. And here is the overview of our system. There are mainly two components. One is about the offline model training, and the other is about the inference process. In the learning process, we extract the frequency and time domain features and design end-to-end models with the power of the deep learning. And then in the inference process, we segment the input sequence and then select the corresponding model to do the interpret. And then the sign language will be translated into text and followed by a voice translation. To give more key techniques about our work, we find that for the same signs performed by different signers, the sensing data will be different, which actually indicates the wide spectrum of the signs. And so in our work that we want to leverage the power of the deep learning to learn the high-level features and semantically to represent our sign language. And the reason why we did not use the DTW technique here is because it's time-consuming to generate a standard template for each specific sign. And in our work, we collect a sequence of data in any directions, and from each involved sensor, then we can generate inputs like this is a three-dimensional data matrix. We then extract both the frequency spectrum and the time domain features from the inputs. To do that, we first use the common filters and the moving average to to remove some noise, and that's have the power band produced by the fast FFT, and then based on this, we can utilize the fast FFT coefficient to generate a spectrogram, which represent the signal stress of data at different frequencies over time. And here we want to show the power of using the LSTM network to extract the common feature of the same sign gesture. The same sign performed by different individuals have a similar descriptor here. The descriptor here can be considered as the output of the third layers of the LSTM in our example. And for the continuous sentence recognition, we need to segment sentence into words. Given a T-length input sequence, we have K label. Each label stands for one specific sign, and plus one more label for the non-sign gestures. And note that different alignments when concatenate all labels. For example, for an input line, for an input sequence whose label is ABC, we may have different alignments like this one. We have repetition and also have the black label. And then we can use the synthesis technique to segment words during which we will merge the repetition of labels and eliminate the blank. And after that, we can get the same alignment like this. And more specifically, the output vector can be considered, can be interpreted as a probability at time t, and that the SL star here represent all the possible alignments. And synthesis then will minimize the negative log probability of the output of the target transcription label sequence. And in the inference process, we rapidly segment the signal by detecting a pulse and a huge jitter triggered by movement of hands and fingers. And specifically, given the T-length signals, we will set up a slide windows and then calculate the variance of the involved difference vector of the magnitude values. We segment this value if the variance is less than the threshold. That after that, we can select the corresponding module based on the length of the segmented sequence, where the word level has a much smaller value. And in the following, I want to show the high accuracy and the efficiency and the robustness of our system. We actually select 103 common use words and generate 7 free common use sentences, which follow the grammar of American Sign Language and have various transition information. We adopt the word error rate here to measure the accuracy, and the WR of the translation system should be as low as possible. So here is the result of our system, and it shows that the average WR of our recognition system is about 1.04%, and there's no huge big difference among the performance of different sentences in which we involve sentence vary from 2 to 11 words. And we also show the processing delay here. For a sentence with 11 words, which we have the delay is about 1.1 seconds, and the average translation speed for different sentences is approximately less than 1 second. And they also measure the impact of some unexpected body movements. And our results show that with this different body motion, such as sitting, user is sitting, standing, walking, or turning body around, that will have some impact on our system performance, which will change from around 1.6% to 12% respectively. And I want to conclude our work. We propose the first SmartWatch-based end-to-end sentence-level American Sign Language system, which is more comfortable, portable, and user-friendly, and offers accessibility anytime and anywhere. And our system still have some space to improve. First is that, as mentioned before, there are some practical issues, such as if users are working, that will impact our performance, and also it will be time-consuming if we want to collect a large number of data to train a user-specific model. So to fine-tune a generic model for each user will be a better choice in our future work. Okay, thank you for listening, and I'm happy to take questions.